All right, so yes, my name is Marco. I'm a faculty in the Department of Aeronautics and Astronautics. So the goal of my research, as just mentioned, is to develop autonomous systems. In particular, is to design decision-making algorithms to make robots capable of making decisions on their own. In other words, the goal of my research is to enable the transition from the world of automation, whereby robots operate in scenarios where tasks are repeatable and very predictable, to the world of autonomy, where robots need to respond to situations that cannot be foreseen at the design stage, and therefore they require some form of reasoning. Now, the field of robot autonomy is booming with many different applications, from autonomous cars, which are, of course, one of the most celebrated examples in the field of robot autonomy, to automated vehicles to transport goods and groceries, to unmanned aerial vehicles. And not all autonomous robots need to be mobile. For example, surgical robots that are currently used in hospitals are poised to become automated. That is, no longer needing teleoperation from doctors. Now, a key application domain for my work is represented by ground autonomous vehicles, that is, self-driving cars. And here at Stanford, I direct the Center for Automotive Research at Stanford Cars, which is a center that brings together about 20 different companies operating in the future mobility ecosystem, from self-driving car startups to insurance companies to cities to suppliers and so on and so forth. And in this center, we work on a number of aspects related to vehicle autonomy, from vehicle control to decision-making under uncertainty, AI safety, perception, and so on and so forth. Here is an example of our research. Actually, this is research done by a colleague of mine, Chris Curtis. So here you can see a vehicle that is going to perform drifty maneuvers in a completely automated way. And here the idea is to assist drivers in situations whereby you are on the verge of losing control. Here there is also the sound if you want to hear the tires screaming. So here the students got a little bit excited. So what is interesting about these videos is that here we are achieving superhuman performance. That is, it will be very difficult, actually impossible, for a human to drive in drifty conditions in such a repetitive way. You can see how precise these trajectories are. But to give you a more concrete idea about how much investment there is in the V technology and more broadly in the field of future mobility, let me show a few slides that showcase the establishment of R&D centers in the field of vehicle autonomy and future mobility here in the Silicon Valley. Specifically in this map, you can see the Bay Area. You can see Palo Alto, where we are now, and then you can see the Bay. And this is the situation in 2014. So traditionally, until about 2010, the Silicon Valley was not really interested in automotive and in mobility. And in 2014, you can see that just a handful of companies have an R&D presence in the Silicon Valley. So here you can see Ford, BMW, GM, Tesla. The numbers at the bottom of the logos represent the square footage of the R&D centers to give you a sense of magnitude of the investment. So a couple of years later, the ecosystem is much richer, with the addition of a number of suppliers, startups such as Zoox. And since then, the growth has been exponential, with several new companies being established pretty much every month. July, August, September, October. So now we're in 19. So this is my last map. And what is amazing in this map is not just the sheer magnitude of the sheer number of companies that have a presence in the Silicon Valley working in this field, but also the diversity of players covering OEMs, startups, suppliers, mobility companies, insurance companies, and so on and so forth. Now, in the past couple of years, there has been some consolidation among the players, but certainly the level of investment is still extremely high. Now, I've been fortunate to be part of this ecosystem for the past 10 years or so. For example, I was one of the early advisors of Zoox, which is a self-driving car startup that has been recently acquired by Amazon. And currently, I'm fortunate to lead autonomous vehicle research at NVIDIA. NVIDIA is indeed has indeed one of the most ambitious programs in the field of vehicle autonomy, spanning both hardware and software. And here, I'm showing the 5 pillars of the NVIDIA V program, from data ingestion to mapping, simulation, AV driving, and basically simulation in the cloud. And each of these pillars actually is poised for significant research. Now, progress correspondingly has been mind-blowing. At least here in the United States, the field of autonomous driving has started in 2002 to 2005, 2006, when DARPA decided to establish some by now celebrated competitions referred to as DARPA Grand Challenges. Here on the left, I'm showing some video snippets from the 2005 DARPA Grand Challenge. And you can see how the vehicles were very tentative in the way of moving around. Perception was not really at the level of accuracy that we need. Vehicles were getting confusing very easily. Some people tried to win the competition with motorbikes. That didn't really work out. So that's the state of the art in 2005. 12 years later, we see a cruise vehicle driving autonomously at night in the streets of San Francisco. So you can see just in the span of 10 years how much progress there has been. We're not there yet, but the progress has been quite phenomenal. Now, this was just a qualitative video. More quantitatively, how do you track progress? Well, there is no perfect metric, but one metric that is often used is represented by the disengagement rate metric. That is how frequently a safety driver has to take control of the autonomous system because the autonomous system is misbehaving. So here I'm showing a plot about the disengagement rate by Waymo vehicles. Waymo is the branch of Google working on self-driving cars. And you can see that in 2018, the disengagement rate was 0.1 over 1,000 miles, so roughly once every 10,000 miles, which is a significant engineering feat. And of course, now the performance is even better. Now, of course, this metric has some pitfalls that we can discuss offline, but I think it conveys the message that the field is making progress. But we're not there yet. So what I want to discuss in the next few minutes is some of the open problems in the field, particularly as it relates to the deployment of AI technologies in modern autonomy stacks. And the first topic I want to discuss is how people are leveraging AI for the purposes of human modeling, and what are the key technical challenges. In general, human modeling is critically important in order to develop autonomous vehicles, both for the purposes of real-time decision-making. In order to drive around, you need to forecast what other humans on the road are going to do, typically in the next 5 to 10 seconds, and then plan actions that anticipate possible reactions. But you can imagine how many different situations you can encounter, and on top of it, driving is a very location-specific phenomenon, meaning that the way people drive here in the United States is very difficult, for example, from the way that people drive in Italy from where I'm from. An anecdote that I like to say sometimes is that, for example, if you go to the north of Italy and you blink your lights, that is a kind sign. It means that I'm yielding to you and you can cut in front of me. But if you go to the south of Italy, which is about 800 kilometers south of the north, and you blink your lights, that is actually an aggressive sign. It means that don't you dare to cut in front of me because I'm not going to slow down and we're going to crash. And an autonomous car has to reason about all this nuanced behavior of a human. And we had to do that. Like, to show you why we had to do it, let me show you a video of a Waymo vehicle here driving, allegedly autonomously, that is trying to merge onto a highway. Now, the vehicle is going to display the light signaling that it wants to merge on the highway. But as you can see, none of the human drivers on the highway are really opening up a space for a Waymo vehicle to get onto the highway. And the autonomous vehicle is not aggressive enough or proactive enough to find the space, and then at the end of the day has to give up and then exit the highway and probably try again. So this is a case where the vehicle is perfectly safe. There was no accident. But from the point of view, this behavior would be, from a product standpoint, a disaster. Nobody would like to ride in a vehicle that has to try 10 times before merging onto a highway. So the point here is that merging into traffic is really an exercise in negotiation. And autonomous vehicles should be able to perform such negotiations for safe and efficient driving. So in my lab and in the community at large, we're working on embedding different ideas, for example, from deep generative modeling, in order to enable a capability that I refer to as a proactive decision-making, which basically entails proactively interacting with other agents to infer their intents, while concurrently exploiting this information to take actions that account for possible responses. So this is, in my mind, one of the grand challenges for the ecosystem. And not only for the purposes of real-time decision-making, but even more for the purposes of a simulation. Simulation is in many ways the holy grail for robotics. If we had a good simulator and we could actually engineer a robot in simulation, the development cost would be reduced dramatically. But for example, in the context of autonomous vehicles, simulators are used, but not as much as you would like to think. And one of the key reasons is that we don't have a good way of emulating humans in a simulated environment to really realistically stress test an autonomous vehicle. So still, this is a big open problem. Now, as I mentioned, AI in general is becoming a key component of modern autonomy stacks because of the capabilities that it offers. But on the other hand, it also creates some challenges. And in particular, it's very hard to make any sort of safety claim when you have machine learning models in the loop. And just to make sure that we're on the same page, so the typical process to train a machine learning model, given a machine learning model, is to take a data set and train a model with the idea that hopefully this model will generalize to new cases that are not represented in the data set. And this approach typically works extremely well. And this is the reason why machine learning models are at the core of modern AV stacks. But providing safety assurances for such models represent a major challenge. Here is an interesting example of a picture of a stop sign, if you can see on the right-hand side of the figure. And so this stop sign is on a billboard. And the stop sign on a billboard fools the perception system of the Tesla autopilot and causes a ghost brake, which is a very dangerous event. So a ghost brake is basically a braking maneuver with no apparent reason. So this is a case where the machine learning model basically was fooled by a situation that was very different from what was seen in the training data set. So more broadly, no matter how well a machine learning model is trained and optimized, it can still perform poorly as it might encounter situations that are very different from those seen at training time. So what we are working on in my lab is to equip deep neural network models with monitors that constantly monitor the level of confidence of the neural net model and raise an anomaly signal in case the neural net model is operating outside its domain of expertise. Let me show you an example of our technology applied to the setting whereby we have an aircraft, in this case, that is taxiing on a runway by using a machine learning model to take images and input and then produce an estimate of lateral displacement with respect to the center line of the runway as an output. And then based on that estimate, compute an action to track the center line of the runway. So on the plot on the right, I'm going to show you the health signal of the machine learning model. On the x-axis, we have time. On the y-axis, we have, in a way, a measure of health. The model was trained in clear morning conditions. So when the model sees images in clear morning conditions, the health signal is low, as you can see here. But now we're going to transition into an afternoon condition, as you will see very briefly. Here, where you start seeing shadows. These shadows were not really represented in the data set, so this confuses the machine learning model. But fortunately, this condition is picked up by the monitor, which basically tells the decision-making module, look, the output of the machine learning module should not be trusted. It's probably a good idea to consider a contingency maneuver. Now, you might wonder, why didn't you consider afternoon conditions as part of the data set to train the machine learning model in the first place? Of course you would. So this is just a toy example to show how things work. The idea, though, is that no matter how many training examples you have, you're always going to have some surprises. So this is a technology we have developed in order to reason about those surprises in a safe and efficient way. And actually here at Stanford, I'm leading a NASA-funded center on a safe AI, where we look at the development of these technologies along many different aspects. So very quickly, let me conclude by saying that autonomous vehicles are just one of the many new technologies that are poised to disrupt, to use the term of this seminar, of this event, to disrupt the mobility ecosystem. But there are many more. The idea of the shared economy, specific purpose design, the idea of connecting all the vehicles and centrally route them in order to optimize throughput, electrification of the powertrain, and so on and so forth. How to blend all these technologies is still a bit of a question mark, which is also a little bit of an opportunity. In my lab specifically, we're looking at the three main themes. First, how to devise reinforcement learning-based algorithms to coordinate very large-scale fleet of possibly automated vehicles by taking, for example, into account couplings with other modes of transportation or the power grid. Second, we're looking at ways to include equity objectives in the control of transportation systems. And finally, in order to control a system, you need to observe it. And observing a transportation needs system means that you're gathering privacy-sensitive transportation data. So we're looking at ways to extract, in a privacy-preserving way, transportation information from a mobility system, and then use that anonymized data in order to control the system. With that, thank you very much for your attention. I'd be happy to answer any questions you might have.
Questions from the audience? Up and saw the first one in the back, and then we'll come forward.
Thank you. Hi. I really enjoyed your talk. Thank you. I have a question about how you apply the reasoning from that example that you gave. There are so many different anomalous situations that can happen on the road, and some of them happen really rapidly. So is the idea that adding this sort of notification that the confidence is quite low on a specific situation, and that the human driver should step in and take the wheel. I know that there's some question about whether or not that's actually safer, because humans sort of being jolted out of whatever they're doing to all of a sudden grab the wheel and figure out what's going on can itself be a dangerous thing. So is the idea that you would construct a system that alerts drivers in a safe way? How would that operate in a situation where it's like a split-second decision that needs to be made?
Yeah, that's a good question. So first of all, it can be used in a couple of ways, either in L2, L2+, L3 context, whereby you alert a driver, or in a completely L4 automated context, whereby you're not alerting the driver, but you're alerting the downstream decision-making module in order to enact a contingency maneuver. So how basically to balance the fact that you have low confidence in your estimate of the word, and the fact that possible interventions might make the situation even worse is an extremely difficult engineering question to ask. It's a delicate balance between competing objectives, and here there is like no silver bullet. It requires basically making the downstream, making logic parameterizable, and then find good parameters that trades off the different objectives in some optimal way. But this is true across many, many different functions. I mean, this is a kind of inherent misalignment between objectives. For example, one of the most critical and basic advanced driver assistance systems is automated emergency braking. And there, you are constantly trading off the detection of an object with the fact that that object could be a false positive, and it could give rise to a ghost break. So how do you trade the two? The two is a painful process of calibration of your machine. But the point is that you make your model, downstream decision-making module, of enough capacity so that hopefully you have a right sensing of the parameters so that you achieve really the sweet spot.
Super. And there was a question over here. Yes.
How many years will it take, you estimate, until we all have cars without steering wheels?
Without anyone on the road?
Just completely stopped by cars.
That's a billion-dollar question, right? Well, so we do have actually autonomous cars on the road without safety drivers providing service. So for example, Waymo has deployed a ride-hailing system in the city of Phoenix and more recently in San Francisco, where customer can get a ride, and there is no safety driver on board. But these are very small deployments, so we're talking about the hundreds of vehicles. So the name of the game, if you want to be profitable, being a company, is how do you scale this business at a scale that is enough to turn a profit? And that's really the engineering challenge right now, which basically is cross-cutting. It goes from how do you reason about massive amount of data to fine-tune your models, to make the models adaptive enough to be easily deployable in new communities, with new weather conditions. So it's going to be a very incremental process. Right now, we have a proof of existence where at least a few hundreds of vehicles are operating autonomously. Well, when the penetration of this vehicle will be at, say, 50%, honestly, nobody knows. But arguably by 2030, at least there will be several installations across the United States and China where it will be possible to drive these vehicles. But that said, vehicle autonomy is not just full autonomy. Like for the case of advanced autopilots, such as Tesla or NVIDIA, those are going to become widespread in 2 to 3 years. And that has a much clearer roadmap.
Thank you very much.
Right.
Thank you very much.
Thank you.